Dear students, I am Dr. Amir Fawazur, and in this series of videos we will learn different heterocycles, and today's topic is Furan. Furan is a five-membered oxygen containing heterocycle. In this five-membered heterocycle, all atoms lie in a plane and form a slightly distorted pentagon. Now we learn the synthesis. There are different pathways to synthesize furan. First method is Paal-Knorr synthesis. In this method, 1,4-dicarbonyls undergo cyclodehydration and as a result furan derivatives are obtained. In this case particularly 1,4-diketones are used. For example, we have this 1,4-diketone, 1,4 because with respect to the position of functional group relative to each other. This is not a nomenclature numbering, rather it's relative positioning of two functional groups. And this 1,4-diketone undergoes cyclodehydration in the presence of concentrated sulfuric acid, and we get furan derivative. Now we try to learn the mechanism. In the first step, protonation takes place, and because both the carbonyl oxygens are equivalent, so any of them would take the proton and would get protonated. This can be expressed in this way or represented in this way, as well as these electrons can go here. So we get positive charge here. Now in the next step, this bond shifts here and this attacks at this place. As a result, we get the cyclic structure. In the final step, loss of water takes place once again. So we get 2,5-disubstituted furan. So I explain the mechanism once again. In the first step, the carbonyl oxygen takes a proton and gets protonated. As a result, we get protonated carbonyl, which resonates like this. Both forms are okay, and this bond shifts here, proton is lost, and this double bond attacks at this position. Same can happen here. This bond can shift here and this can attack at this position. This bond would come here. As a result of using both the forms, we will get the same structure, and then in the last step again water molecule would be eliminated and we would get furan derivative. So this was first method, Paal-Knorr synthesis or Paal-Knorr synthesis. Next method is Feist-Benary synthesis. In Feist-Benary synthesis, we have alpha halocarbonyls which react with beta-ketoester. For example, this is R1, this is R2, this is R3 in the presence of base, and as a result we can get this. Now we see the mechanism. In the first step, beta-ketoester reacts with base sodium carbonate and enolate is formed. This enolate reacts with carbonyl group of alpha halocarbonyl, and this bond, the negative charge attacks here, this bond shifts and transforms into a negative charge on oxygen, and as a result of protonation or quenching or taking proton from the reaction medium, it is converted into corresponding alcohol. So we get this one, and next proton from here is abstracted and this bond attacks here. As a result of this reaction, we get this, and in the last step, proton, this water molecule is eliminated, minus H2O, and we get Furan derivative. So this is position 1, position 2. Whenever we have heterocycle, atom gets number 1, then 2, 3, 4, 5. So this is basically 3 fluoric acid derivative. R1, R2 are 2 other substituents. So we get 2, 3, 4 tri-substituted furan derivative in this case. So I explain the mechanism once again. In the first step, enolate formation occurs in the presence of beta-ketoester, which reacts with sodium carbonate, and this enolate which is formed reacts with carbonyl group of alpha halocarbonyl, and as a result we get this intermediate, and in this proton is abstracted from here, this bond shifts here, and double bond from the carbonyl group attacks on this carbon. As a result of this SN2 nucleophilic substitution reaction, we get this molecule, and in the last step dehydration occurs, water molecules is eliminated, and we get 2, 3, 4 tri-substituted furan derivative. So this was the mechanism. Now this reaction was explained with the general example. Now we take a specific example. For example, 1,3-diketone reacts with chloroacetaldehyde, and in this case, in the presence of base, again sodium carbonate, we get this type of furan derivative. Now we see the mechanism. Again, in the first step, we have this diketone which is treated with the base, for example sodium carbonate, and we get the enolate. This enolate reacts with chloroacetaldehyde, it attacks here, this goes upward and takes a proton, and as a result it is converted into this, and in the next step this proton is abstracted, the bond shifts here and this double bond attacks here, and we get this double bond here, and in the next step again this water molecule is eliminated, and we get furan derivative as a result. So I hope this is clear. Now this reaction is also affected by reaction conditions. We now see how it is affected. For example, we have this ketone, or we see chloroacetone. We have chloroacetone and we react it with methyl acetoacetate, or for example ethyl acetoacetate. When they are reacted in the presence of, for example, sodium ethoxide in ethanol, and in the presence of sodium iodide, as a result of the reaction we get this halogen replaced and we get this. So in these conditions the enolate which is formed here reacts with this carbon first and we get this, and this can be cyclized, for example in the presence of oxalic acid, to form 2,3,5 trisubstituted derivative. And if the reaction occurs in sodium hydroxide aqueous conditions, the enolate attacks again on this carbonyl carbon, and we get this derivative, and again all the mechanism would be same which we have discussed earlier, and final compound would be So we can see if we have different reaction conditions, we can have different regiomeric products. For example, in this case we have 2,3,5 trisubstituted furan, and in this case we have 2,3,4 trisubstituted furan. So this was Feist-Benary synthesis. Now furan derivatives can also be prepared from oxazoles. We have this methyl substituted oxazole derivative. And we react it with diethyl acetylenic dicarboxylate. So this reaction is 4+2 cycloaddition reaction, where this is reacting as dienophile, and here we have diene, so we will get 6-membered ring. This is the oxygen bridge. And we get this. So again, this bond shifts here, this bond shifts here, this bond shifts here, and we get CH3CN plus furan derivative. So this is, in the first step we have cycloaddition reaction between oxazole and diethyl acetylenic dicarboxylate, and in the second step we have again 4+2 cycloreversion, and as a result we get furan derivative. So these were some methods for the synthesis of furan.